Hello AP Chem, this is Mr. Coker. 6.C.2 homework. First question was 16.10, which asks which combinations are good buffers. Remember, to be a good buffer, it has to be a weak acid conjugate base pair. And potassium cyanide, hydrogen cyanide, will be a good buffer because HCN is hydrocyanic acid, which is a weak acid, and CN minus from the KCN would be its conjugate base, and K plus would be a spectator ion. So a mixture of a weak acid and its conjugate base is a good buffer. Sodium sulfate and sodium hydrogen sulfate. Now this one's a bit controversial. The book would say that yes, this is a good buffer because HSO4 minus hydrogen sulfate is a weak acid and sulfate minus 2 is its conjugate base. But remember, AP considers H2SO4 a strong acid, which implies that they believe both H's are strong. Technically, the second Ka for H2SO4 is 1.2 times 10 to the minus 2, so technically it is a weak acid, but we should go with what AP says, that HSO4 minus is a strong acid, so then we would say that no, this is not a good buffer because it's a strong acid and its conjugate base. Ammonia and ammonium nitrate. In this case, nitrate would be the spectator ion, ammonium would be the weak acid, and ammonia would be its conjugate base. And so yes, this would be a good buffer. And finally, sodium iodide and hydroiodic acid. Hydroiodic acid is one of the 6 strong acids, so this will not make a good buffer with iodide. 1612 uses the Henderson-Hasselbalch equation, pH equals pKa plus log of conjugate base over conjugate acid molarity. And so since the Ka of acetic acid, CH3COOH, is 1.8 times 10 minus 5th, and both the acetate from the NaCH3COO and the acetic acid have a 2.0 molar concentration. The pH would be 4.74 plus the log of 2 over 2, and the log of 2 over 2 is 0, so 4.74. If you change the molarities to 0.20 or 0.20, you still get a pH of 4.74 because the ratio is still 1 and the log of 1 is 0. However, the 2.0 molar buffer will be more effective because it will have a higher concentration of weak acid and conjugate base, and those would be in reserve to neutralize any added base or acid. And so if you added base or acid, the A minus over HA ratio would change less in the 2 molar buffer than in the 0.2 molar buffer. We would say the 2 molar buffer has a greater buffer capacity. 16.14 gives a buffer which is composed of dihydrogen phosphate, a weak acid, and hydrogen phosphate or monohydrogen phosphate minus 2, the conjugate base of dihydrogen phosphate. So I went in the textbook and I looked up the Ka2 of phosphoric acid, and it was 6.2 times 10 to the minus 8. So the pH will equal the negative log of 6.2 times 10 minus 8 plus the log of 0.1 molar, the molarity of the conjugate base, HPO4 minus 2, over 0.15 molar, the molarity of the dihydrogen phosphate. So in the end, we have 7.21 plus negative 0.18, or a pH of 7.03. Notice the pH is lower than the pKa of 7.21 because we have more of the weak acid than we have of its conjugate base. 16.18, we're back to acetic acid again. This time we have 1 liter of a 1 molar solution, which means we have 1 mole of both the acetate and the acetic acid molecule. So our pH is equal to 4.74 plus, if we were to add 0.08 moles of sodium hydroxide, that would increase the molarity of the A minus to 1.08 and decrease the molarity of the HA to 0.92 because it would react with HA to convert it to A minus. So now we have pH equal 4.74 plus the log of 1.08 over 0.92, which is 0.07. So 4.74 plus 0.07 equals 4.81. The added base has raised the pH by 0.07 units, which is actually a very small amount because of the buffering ability of the solution. In B, we simply do the opposite. We take 0.12 away from the 1 molar A minus, and we convert A minus to HA, so HA is 1.12. So now we have a pH of 4.74 plus negative 0.10, or 4.64. The added acid has lowered the pH by a small amount. Finally, 16.38 asks what happens to the indicator, or rather what pH the indicator will change color at. And if you recall, we can use the Henderson-Hasselbalch to analyze the pH of indicators. The indicator will be half acid color and half base color when its pH is equal to its pKa. The negative log of 2 times 10 to the minus 6 is 5.70. So our solution starts out acidic, so it'll start out green. When the pH rises to 5.70, it will transition from green to red. So 5.70 would in fact be in the region of the vertical part of the pH curve. So this would change color at the equivalence point of the titration as sodium hydroxide is added to hydrochloric acid. But to answer the question, it would be at a pH of 5.70.